patterns when we do our polynomial multiplication. And the first problem set is all about multiplying binomials that have what we call alternating signs. And I'll use a simple example. I will go with n plus 5 times n minus 5. So the binomials are identical almost. They both have n and n, into the 1n, 1n, and then the constant is 5 and 5. The thing that differs, though, they have alternating signs. This is positive 5, and this is negative 5. So when I perform my distributive property multiplication, I end up with n squared minus 5n plus 5n, and then I have positive 5 times negative 5, so my constant is negative 25. When I combine like terms, when I combine the linear terms, you can see that they're additive inverses, so what remains behind is n squared minus 25. And this is what we call a difference of two squares. Difference is subtraction. Even though we have redefined subtraction as the addition of a negative number, you're still taking the difference between two. And then this term is a perfect square, and 25 is also a perfect square. And in class, we'll talk about how you determine whether or not a variable is a perfect square. But if the power is even on a variable, then it's a perfect square, meaning n to the sixth power, just to make an example, could be thought of as n cubed times n cubed. So when I can take the power, if it's an even power, that means I can divide it by 2, and I would have had that variable raised to a number times the variable raised to the same number. And that really is the definition of what a perfect square is, the same number multiplied times itself. And we will talk about that in class more. But you can see the exercise set on this page. The binomials are identical, and they have what we call alternating signs. So I just want you to get comfortable with multiplying these out and recognizing the pattern. And you can see it's a very consistent problem set, so there should be no surprises. But go ahead and do the problem set so that you get this ingrained in your memory, and that way you can just quickly recognize the patterns. The second problem set for the evening, or for Monday, is what happens whenever you take a binomial and you square it. So now, instead of having the alternating signs, it is the same binomial times itself. And when I multiply this out, I get the n squared plus 5n, and then plus 5n again. And then my constant is always 5 times 5, or the last two numbers, giving me a perfect square. And when I combine like terms, the linear term remains n, and it's just simply whatever the constant in the original was plus itself. But you can see that this is what we call a perfect square trinomial. Trinomial because I have three terms. I have a perfect square in the constant, and I have a perfect square in the quadratic. And the square root of the constant, so the square root of 25 is 5. And the coefficient on my linear term is this square root times 2, or this square root plus itself. And it's what we call a perfect square trinomial. So your homework set is multiplying these out, seeing this pattern. So, here, well, there's n plus 5 squared. I did the first one for you. But go ahead and do these so that you can recognize what happens. You can see it's a very consistent problem set. So you're just taking the binomial and you're multiplying it by itself, or you're expanding it. And then what happens in the second set of problems is the more interesting part of the homework. You're actually given problems, and you have to determine whether or not they represent perfect square trinomials. Is the trinomial a perfect square? So you could look at a problem like number 21, a simple problem. You have an even power in your quadratic, so that is a perfect square. 9 is a perfect square. The square root of 9 is 3. And then you look at the linear term. The coefficient on the linear term is 6. Is this coefficient, whatever the square root was, times 2, or plus itself? So is the coefficient 3 times 2, or is it 3 plus 3 when you're looking at the linear term? So that's how you determine if you're looking at a perfect square trinomial. Not all of the problems in the problem set are perfect square trinomials. Let's look at number 26, for example. I have a squared term in my quadratic, so that is a perfect square. 144 is also a perfect square. 144 is 12 times 12, so the square root would be 12. But the coefficient on the linear term must be 12 plus 12, or 12 times 2, or 24. So the example in number 26 is not a perfect square trinomial because the coefficient on the linear term is really 12 times 1, or just simply 12. So the homework is very consistent and predictable, and it's all about getting you to recognize the patterns with the binomials.